So again, we'll start off by writing out the formula. Oops. Formula always uses function notation. So in our case here, our function is 3 root x. So we start by replacing every x with x plus h, so that'll be our first function, minus f of x, which would be 3 root x, all divided by h. Suggestions? Yes. This is one where we're going to multiply by the conjugate. So anytime we see square roots, this is often a strategy that we're going to have to use. On the bottom, we'll leave it factored. On the top, since this makes a difference of squares, we can multiply that out. Again, going from the top from here to here, if you're not comfortable with the difference of squares as a shortcut, which is basically this idea that when I have two conjugates and I multiply them together, what happens is the first one gets squared, the last one gets squared, and there's a minus sign in between. So that's all I did here. To get 9x plus h, I multiplied 3 root x plus h times 3 root x plus h. And the 3 times 3 is 9. And the square root times the square root will cancel each other out, and you'll just get x plus h. Same thing with the last one. 3 root x times 3 root x, well, 3 times 3 is 9 again. And then the root x and the root x will just become an x. So now at this point, if you multiply out the top, you'll get 9x plus 9h minus 9x. Are you okay if I just write 9h? And now our h's can simplify. And we can evaluate our limit. So I don't need to write limit anymore. And then 3 root x plus 3 root x is 6 root x. Now, if you were looking in your textbook and you were trying to simplify it, your textbook's answer probably won't look like this. They'll have it simplified already. They'll have their answer look like, most likely like that. So how do you go from the final answer in blue to the answer that's in the back of the book that's in green? You're going to have to simplify the fraction, right? And then rationalize. So you have to multiply by root x and root x. Yes? So you're getting started here. You're plugging it into the definition of the derivative. I'm going to hide something here so you can't see all of it. Whoa, that's a circle. That's not what I wanted. I'm going to hide this right now. There we have our definition of our derivative. Oh, you can't see that because my screen's frozen. Okay? That's plugging it into your definition of your derivative. You have to plug in an x plus h wherever there's an x. So make sure that you plug in an x plus h for the first one and an x plus h for the second x. And now we have to use our algebra to expand each of these. So if you want to see if you expanded the x plus h cubed correctly, here you have x plus h, x plus h, x plus h. So you'd multiply two of them together first and get x squared plus 2xh plus h squared. And then distribute that again. Combine all your like terms and you'll get x cubed plus 3x squared h plus 3xh squared plus h cubed. And I said before, if you remember Pascal's triangle, the 1, 3, 3, 1 matches up with the coefficients of each of those. And your x variables, the exponent's going down by 1, and your exponent of h is going up by 1. So you get x cubed plus 3x squared h plus 3xh squared plus h cubed. And now you can plug that back in to your formula and have it look like this. So once you've expanded everything and combined like terms, what you're left with in your numerator only has an h in common in all of them, which means you can factor that out. And once you've factored that out, then you can apply the limit. Wherever there's an h, you can plug in 0 for h, and you will just get 6x squared plus 4. So here's the next one. Start by plugging that definition of derivative in. And just to check to see if you've got your definition of derivative correct, this is what it should look like. So yes, we have a complex fraction. Our strategy right now is to try and get a single fraction, and we can do that by trying to get a single fraction on the top. So we need a common denominator. What will that look like? We'd have to multiply, and I multiplied the 2 through the x plus h, so I wrote 2x plus 2h minus 1. But then to get a common denominator, the first fraction is going to need a 2x minus 1 on the bottom. The next fraction is going to need the 2x plus 2h minus 1. Whew. So next, whoa. It's really liking me here. I'm just going to get rid of it. Sorry about that. So next, if we multiply out the top, and we have a common denominator now of 2x minus 1 times 2x plus 2h minus 1. And we multiply the first fractions, and I put them in square brackets here. And we multiply out the second set of brackets, and I put them in square brackets as well. Now it's important we keep things in brackets because right in between here we have a minus sign, and that means we're going to have to subtract everything to the right of that minus sign. So those brackets are really important, because most times you might be tempted just to subtract the first term and forget to subtract the other terms. And once everything is multiplied out, you notice there's a lot of things that are going to cancel out. And so I started putting a line through some of the things that cancel out there already. What we've done is we've got now really big, but a single fraction on the top. And on the bottom with the h, we can think of this as h over 1 if we'd like, and we have a single fraction on the bottom. And what do you do when you have a fraction divided by a fraction? You can multiply by the reciprocal. Can you see that the reciprocal would be 1 over h? And when you multiply by 1 over h, the top is going to stay exactly the same, and all that's going to happen is our h is going to get multiplied on the bottom of that fraction. So that's going to look like this. So I have the bottom of my fraction, I now have an h on the bottom there. And after I simplify everything away from the top of my fraction becomes negative 5h. Which is really handy because then our h's will cancel out, which was our goal all along. And once those h's cancel out, you can now apply the limit. You can plug in 0 for h. On the bottom, you'll have 2x minus 1 times 2x minus 1. So I've written it as 2x minus 1 all squared. And that is our final derivative. We wanted to find f prime, so we have found f prime of x to equal this.